Hello class, today I'm going to talk about turbulent flows, what is the turbulence, and give you a little bit introduction about turbulence because we don't have enough time during the lectures to talk about that, and this topic is a bit advanced, but because you are using Fluent for your simulations, you should have the basic understanding of the turbulence flow. People usually call turbulence as a last great unsolved problem of classical physics. And as you can see in this writing, this is the last one. Physicists hasn't start solving it. And one of the challenge we have as engineers is turbulent flows. Usually they're unsteady and periodic. They have a unsteady and periodic motion, so time dependent. Because of their turbulence and eddies, they are mostly 3D. So if you want to have a turbulence flow investigation for your project, for your thesis, that simulation must be 3D, so it takes long time and a lot of mesh. So you need to have a good computer, strong dependence on initial conditions, and finally we have wide range of scales. Later, gradually, you are going to understand these terms. Let's start what is about when we are talking about laminar and turbulent flow. Okay, we have a cylinder like this. This is our cylinder. And there's a flow from the left side, and as you can see, streamlines are very smooth without any eddies or any circulation. This happens for Reynolds number under 5. If you increase Reynolds number, gradually you are going to have some circulations here at the top and bottom. It is symmetrical, and this Reynolds number is supposed to be between 5 to 40. Still, our flow is laminar. Although we have some circulations, any circulation or any circular movement in the flow doesn't mean we have a turbulent flow. Gradually, if you increase Reynolds number, you are going to reach to the point the flow is totally turbulent. And as you can see, this shaky line shows we have turbulent flow, and these smaller lines, they are eddies. They have different sizes. Sometimes they are very small, sometimes they are very big, and they created because of the turbulence. And basically they are small area in flow which they have a circular movement, and the size of these eddies, they are very important, because if they are very small, you are going to have very small mesh size to capture that movement. As you saw here, all those different flow from laminar to turbulent, they are all dependent on the Reynolds number. So Reynolds number is a key. Let me give you a little bit more understanding of Reynolds number. Okay, let's see what was the formula for Reynolds. Reynolds was density times velocity characteristic length divided by viscosity. I'm going to rewrite this formula like this: Reynolds number, density times velocity times velocity divided by length over viscosity, velocity divided by length square. and I'm claiming the top part is inertial force or convection force item. Convection term. And the lower one is diffusion or viscous term. Viscous term or diffusion. Okay, so based on these, Reynolds number is the ratio between inertial force and viscous force. Okay, let's write Navier-Stokes equation. Navier-Stokes equation basically an equation which can describe flow motion in fluid mechanics. So let's write Navier-Stokes equation. Okay. I'm writing for 1D case, but you know how to write for 2D or 3D. So density times dV dt, this is transient term, plus V dV dx, convection term, must be equal negative dP dx, pressure term. I'm not going to include any source terms, so nothing there, plus diffusion term, d2 dV dx square. So let me name this diffusion term, convection term, transient term. Okay, as you can see, Reynolds number is the ratio of this convection term to diffusion term. I can rewrite this as mu v divided by 2 times length scale. For this one, velocity times velocity divided by length. So you can see those two in Reynolds number formula. So it's about inertial force ratio and viscous force. Okay, so if I had a pipe like this, for the laminar flow, velocity profile inside this pipe is going to be like this. For turbulent flow, it is going to be like this. So very unstable, we have chaotic movement, and inertial force is the dominant force. So when I'm saying for turbulent flow, inertial force is dominant, which means inside this Reynolds number formula, this one is bigger than viscous force. So Reynolds number is supposed to be very large. If Reynolds number is large, we can say we have turbulent flow. We have some critical Reynolds number, which we, for different shapes and conditions, we can say, okay, example for the pipe, if Reynolds number over 2300, usually we have turbulent flow. If Reynolds number is small, it means inertial force is small or viscous force is big, which makes Reynolds number small, and we are going to have laminar flow. Okay, let's see some pictures for the laminar flow for the exact same case we had here. So as you can see, we have a cylinder inside flow stream from the left to right side, and you can see the flow streams are very smooth, no problem with the flow stream, no chaotic movements. You increase Reynolds number, you can see these circular movements, but they're not chaotic, they're symmetrical, everything is laminar. By increasing further Reynolds number, now you can see the effect of Reynolds number and how inertial force is going to create chaotic movement. Here you can see we have large eddy there, another eddy there, one here, another here, much smaller, ears full with those eddies. So for the turbulent flow, you can see we have large eddies and smaller eddies. Let's see. I'm drawing one large eddy. This is my large eddy, and we said this eddy is created because of turbulent flow, and turbulent flow Reynolds number is very high. When Reynolds number is very high, viscous force is very small and it's not important. As time passes, this eddy is going to get divided to smaller eddies, and then these eddies even they're going to get smaller. And this process is going to continue till killing all those eddies. Basically, viscous dissipation, that parameter we had for Reynolds number, where is it? This parameter is going to get stronger and stronger because it's about viscosity of the fluid, and it tends to stop the flow, that movement. So that parameter gets stronger and stronger as we are passing from this level to this level to this level and this level. When that viscous force gets stronger and stronger, it means Reynolds number getting smaller and smaller. And that viscous dissipation finally is going to kill the turbulent kinetic energy. And we have a name for this, we call it energy cascade. Okay, so we are going to solve this this problem, which is turbulent problem. To solve this turbulent problem, you need to solve that Navier-Stokes equation, which is here. This is our Navier-Stokes equation. And when you're solving that Navier-Stokes equation, your mesh size should cover this level of the eddies, which is the smallest one. Otherwise, you're not going to capture that eddies, which is going to create some error for you. So if you want to use Navier's equation and solve this numerical method, we call it DNS method, direct numerical simulation. So we directly go and solve Navier's equation, and your mesh is supposed to be very small because we have a wide range of eddy scales from very large lengths, characteristic lengths, to very small ones. So your mesh is supposed to cover all those. That is why we don't usually use DNS. It takes long time, and sometimes it's not possible at all, and it's not practical. So to solve this problem, scientists introduced RANS method. What is the RANS? RANS is about simplifying the whole fluctuation and chaotic movement we have. How they usually do it? Let's see. This is my graph, not temperature, for example, velocity. And this is time. because I'm simulating a turbulent flow, I expect to have this velocity, transient velocity there. And you can see it is really chaotic. So using Rand's method, Reynolds averaged Navier-Stokes method, we go find an average velocity, which we call it U bar or V bar. Let me write V bar. And we say the total velocity is supposed to be summation of average velocity plus a fluctuating velocity, which is going to be V prime. So here, for example, this is going to be V prime. By doing this, basically you simplify the whole a lot, this chaotic movement, that fluctuations, all the eddies or circular movements in the fluid to very simple case. Rand's methods are really efficient. They're fast, they're easy to simulate, but they have some problem. Their problem is mainly close to the wall. When we have a no slip condition, Rand's methods, they have a difficulty. So let me introduce a few Rand's method. One of them is K epsilon. Really useful. Many people use it, and for engineering applications it's good enough. Another one is K omega, and many more. We have many variations for these turbulent models, which part of Rand's approach. So K epsilon may have like a 5-6 different variations, and 4-5-6 methods to take care of the area close to the wall. Because as I said, we have problem when we want to deal with the area close to the wall. Let me show you a few a little bit more details. This is the turbulent flow, another turbulent flow, and let's see what is the difference between numerical DNS method and Rand's method. So basically this is DNS. You can see all the details, all the flux eddies are captured. You have many details about that simulation, but it may take like several months or even years sometimes to simulate that with that accuracy. And this one is Rand's method, and you can see it's like a hugely simplified. You don't have that much details about the eddies, fluctuating movement, or waves around this wall. But for engineering purpose, you can see if you want to, for example, if this is a temperature, you can, or pressure, you can know, okay, here you have low pressure. And for DNS result also, we can see we have low pressure there. At this position, we have a little bit higher pressure, and also DNS shows the same high pressure. And finally, here and here, you can see, yes, the overall results are very, they can help us for engineering purpose. No, not that much detail, and Rand's methods, they are very fast. We have several different Rand's methods. Sometimes like a K epsilon or K omega, there are 2 equations to solve, extra 2 equations to solve. Sometimes they have 4 extra equations or 6 or 7 extra equations. And as I said, most of them, they have some variations to take care of the area close to the wall. Let's see what ANSYS provides us. This is viscous models we have for inside this Fluent software. First one is implicit case, which is basically viscosity is 0. Second one is laminar case. And from here to here, we are going to have turbulent models. The first one is one equation model. Usually it's a very simplified version, but starting from k epsilon, which is 2 equation, k omega 2 equation, they are much more widely used. And as you can see, gradually the number of equations increases, 4, 7, and more. Here for k epsilon selected, and in this picture you can see we have 3 different variations just for k epsilon model. The standard one, RNG one, and realizable one. Usually if you work more, you are going to see always realizable is better than standard, and depends on your application, you are going to gradually find your simulation is better for a specific model and variation. And if you go lower, you are going to see, oh, they have near wall treatments, 4 different near wall treatments to improve the accuracy of the result closer to the wall. So these 4 methods, they are going to help us to improve the quality, but still they may not be as good as k omega or the ones with higher equation like a Reynolds stress, which they come with 7 equations, and definitely solving 7 equations is going to take much longer time. And the other side, you are going to see some constants. Usually we don't touch those constants, but if for the academic use, if you have some calculation for the specific your specific case, you can find you may find these constants and change them and to have better quality results. Here I talked about this near wall conditions, so let me tell you what's happening near the wall. Usually RANS methods, we have a little bit difficulty capturing the behavior close to the wall. That is why we define a parameter, we call it y plus. Y plus is going to show how much mesh we have close to the wall, and if you have a finer mesh or more, the number of mesh close to the wall was more, you are going to have a smaller y plus. As you can see, under, for example, 5 close to the wall, this is the velocity, you are going to see we have this type of behavior. And then after, there's another zone, which first one we call it this viscous zone, which is close to the wall, and then buffer zone, another equation we can fit there, and then log law zone. Here it's a linear, it's like a linear, but because it's a logarithmic scale for y plus, this is logarithmic. And then finally outer zone is going to be, so RANS can capture the have a difficulty capturing the area close to the wall. So what we do, if this is a cylinder something, if you have uniform mesh with this size, you're going to see y plus as 30. If you refine your mesh, this y plus close to the wall is going to be, for example, 1, which increases the accuracy of your mesh much more, and simulation is going to have much more trustable results. Okay, let me finish with the last method which we have here, large eddy simulations. Okay, I told you about DNS, direct numerical simulation, RANS method, which is averaging everything, and LES is the last method, large eddy simulations. Remember I showed you energy cascade? We have large eddy, gradually it gets smaller and smaller and loses the energy. For large eddy simulation, the idea is, let's use for some percentage of these eddies, to simulate the large percentage of the eddies with direct numerical simulation, and for the smaller percentage use mathematical models. For example, for this case, I'm going to say let's use direct numerical simulation to simulate this sizes of the eddies. For example, this is 80%, and the smaller ones 20%, the smaller eddies, the last 20%, I'm going to model with mathematical equations. And my reason for this is this larger eddies, they have higher energy because Reynolds number was higher and inertial force was higher, so energy is higher. So basically I'm saying let's have accurate simulations for the case we have very energetic eddies. For smaller eddies, less important eddies, let's model it with mathematical calculation, which is going to create less error for us. So LES helped us to increase the accuracy a lot, especially for combustion studies. They're using LES mainly, but it's not as easy as you think. LES still, it is really dependent on the initial condition and boundary conditions, and selecting the filter to what percentage of the eddies you want to capture with DNS is depends on your selection. And let me show you what is the difference between these results. So DNS, where are you? So let's see. This is from experiment, the first one. Second one is RANS. You can see it's so much simplification applied. We don't have any accuracy at all. Just the overall prediction is going to be okay. But LES, still we have many details of the experiment, and the details are not as much as experiment, but we have enough detail to capture large eddies. For smaller eddies, we don't capture them, and it is going to be neglected for LES. Okay, I hope this recording was useful for you, and see you next time.